and so on. So depending on which level I leave the molecule in, a corresponding amount of kinetic energy will actually surface. The one that is the lowest in energy will give me the highest kinetic energy and vice versa. So I will get a bunch of peaks like this. And what are these peaks? 0 to some vibration level, 0 to some vibration level, 0 to the next vibration level, next and so on. Of course, in this case, if kinetic energy is increasing this way, then it must be, yeah, the lowest must come here, be equal to this. Let us say this is 5, this is 6, and 7. This must be 0, 5, 0, 6, 0, 7, and 0, 8. That's the kinetic energy. 0, 5, which is this, has the largest kinetic energy. 0, 8, which is somewhere out here, will have the smallest kinetic energy. So depending on which level I leave the molecule in, I am going to get a corresponding amount of kinetic energy in my experiment. And what are these level separations going to be? These peak separations, what will they be? They will simply be the separation between vibration levels. So you see, therefore, using photoelectron spectroscopy for the molecules, I am actually getting the vibration level information for the ion, which is quite important. And the very fact I see a progression, immediately what does that tell me? It tells me that the peaks are shifted. And immediately if I know that the peaks are shifted, what's the next information I draw? And I am removing an electron from maybe an antibonding or a bonding orbital, and I shifted it. Supposing there was a molecule in which they had a non-bonding electron, and I kicked out the non-bonding electron, then what would happen to the ion state? Nothing. It would just be there, without any change in the nuclear distance. In which case, the ground state would look like this, the upper state would look like this, and then what am I doing? 0 to 0. I would therefore see a sequence and not a progression. And the moment I see a sequence and not a progression, the immediate conclusion that I draw is that the upper state potential has not shifted. If the upper state potential has not shifted, it simply means that I have driven the electron out of a non-bonding. You therefore see that you can actually get information about the electronic orbital structure for molecules by simply being able to look at these structures. So what you should really keep in mind is, if I gave you a spectrum in which there was a large bunch of bands, another with only 1 or 2 bands, and I ask you what is the information you can draw from this. So the information you will draw is the one that gives me a large bunch of bands is actually an ionization to a state which has shifted out or in. The one in which I have just 1 or 2 bands is actually ionization to a state in which there is no change in internuclear distance, therefore telling me that I have actually removed an electron from a non-bonding orbital in that particular case. Now, just like we told for atoms, when I do for molecules, I can remove this and get one bunch of spectrum. I can remove this or this or this, and you will therefore see that in the entire photoelectron experiment, you will see peaks at different places. And each one actually corresponds to the removal of an electron from any one of these orbitals. And you will be able to see all those as much as the photon that you have used will allow you to see. Meaning, have energy this way, and all the orbitals can be ionized with that photon energy, you will be able to see. But if you want to see somewhere inside the core, then you have to get back and do X-ray photoelectron spectroscopy and look at the core molecular orbitals in that case. You have a question?
So, can we have the exact value of how much is the shift in the upper level?
Oh,
Like
you mean the RE?
Yeah, can we have?
Achha. You remember I told you something in absorption spectrum, right? The same thing. If I have a shift, what happens? I see a progression. Okay, now how would I know how much I shifted? What is this determining, starting from here, which level I will reach over here? Who determines that? Frank-Condon factors, right? The Frank-Condon factors The same thing determines the transition probabilities over here. Starting from here, why do I not go here? I can't go here because the Frank-Condon factors will not let me do it. Why am I going to those levels? Because the Frank-Condon principle tells me, starting from here, those are the states accessible. Okay, so if I take this potential and that potential, and then slide them slowly and calculate the Frank-Condon factors as a function of the R, and see at what position in R it matches with my experiment, I can therefore find out where it is. I can do that. But for that, you have to calculate the Frank-Condon factors first by taking this potential, keeping on top of this. Calculate the Frank-Condon factors and see how many states you can reach. Look at your spectrum and see whether you see that many states. No. You move it until your calculated Frank-Condon factors and your actual spectrum, they match. And once they match, then you know that this separation is what the potential curve has actually suffered as a result of the loss of that particular electron. So this is basically the whole, the basics of the photoelectron spectroscopy. You can do it for atoms and get atomic orbital information. You can do it for molecules and get molecular orbital information. But at the end of the day, this is a pretty neat and straightforward technique to be able to get information on the electronic structure of molecules. Of course, there are a whole lot of other complications that sets in when you actually start doing the experiment, but that's a different story. The basics are basically just this. What I'm going to do is, I'll tell you those complications that you can get. Which is not for your exam, it is just for your information. Let me draw this, but don't go to sleep. Let me draw the conventional board like more of them don't ever look like this, but believe that they are. Electrons here, so on. Now, I come in with a photon, I remove this guy, that's the outermost. I see some photoelectron spectrum, no problem. I remove this guy, and I see a photoelectron spectrum, which is the spectrum corresponding to this electron that's going screaming out, and I measure that. But once I have done that, what has happened here? Oh, there's a little hole out here. There's one orbital that doesn't have an electron. So what do you think can happen? This fellow sees this and then wants to jump it, because now, he was essentially pulled out because when we came to filling the electrons, we simply slapped the orbital on this guy and put him out there. But now that I have removed this electron, this guy wants to jump in. And when this guy jumps in, what happens? Oh, that energy corresponding to that will have to be given out. And that can be given off as light. And when it is given off as light, you can actually measure it. And that's the emission spectrum, or the fluorescence spectrum.
How is it possible that outer one is not removed?
Oh, see, I can remove any one. I can remove the outer one. There's a finite probability of this being removed. There's a finite probability of every one of them being removed. So I can remove, the removal does not have to go sequential. The removal does not have to go sequential.
How do you make sure that inner one is?
You don't make sure. There's nothing you can do to make sure. When you shine light on it, this can go, this can go, this can go. Then provided the energy of the photon you have can remove any of these. The photon energy is such that only this can go. Then you have a control. But if the photon energy is such that it can remove this and this, then this will go and this will go. But it is not both. Because when you do both, then what happens? You are producing a doubly positive ion. And you know what happens to the ionization potential when the first electron is removed? Oh, suddenly to remove the second electron, it becomes very difficult. And therefore to produce multiply charged ion is not so trivial. You really need to get the hell out of this molecule to get the second electron out from the same atom or molecule. So I can remove this, or I can remove this. There's a certain probability. And you have no control. You will see both. But if I remove this fellow, what this guy can do is actually jump in and give me light, and I can actually measure that. And that actually becomes fluorescence or emission. And you see this in a big way when you do X-ray. You remove this guy out here, from here to the core, this fellow will jump all the way in and give me light, and it's called X-ray fluorescence. Shine light, remove the core electron. If you are a photoelectron spectroscopist, you go running after that electron and measuring what the kinetic energy is. But you can say, I forget the electron, I'm not bothered about it, let it go. A hole is created here. And what happens? This fellow jumps here, gives me a photon, I measure that photon. And what is that photon energy going to be? It is actually going to be the energy difference between this orbital and this orbital, right? But the energy difference between this orbital and this orbital is actually going to be unique for different elements. Molybdenum will have a certain value, tungsten will have a different value, iron will have a different value. And therefore, when I shine light X-ray of the same wavelength on iron, molybdenum, tungsten, or what have you, radium, rhodium, whatever, the emission that I get will be very characteristic of that element. Because once this is removed and this fellow jumps, the orbital energy of this, and this is all going to be very, very unique for that given element. And therefore, the X-ray fluorescence that I get will be unique for that given metal or for that given element. What can I use it for? If you give me a metal and say, please check for me whether it is molybdenum or rhenium, all I have to do is shine X-ray, get the emitted light and see what the wavelength is, and compare with known energy differences. I can then tell you, yes, this is molybdenum or rhenium or rhodium. Just like if you saw 589 emission, you know it is sodium. Here I am not looking at transitions in the atomics, I am looking at transitions of electrons from one of the inner levels to something way to the core. And that's called X-ray fluorescence, which is a very powerful analytical tool. And in fact, the amount of X-ray emission you get is actually going to depend on the concentration. Therefore, not only can I tell you that you have molybdenum inside, I will be able to tell you how much of molybdenum you have. Simply because X-ray fluorescence is a wonderful analytical tool. The frequency of emission tells me what the element is, and the intensity of emission tells me how much of it is there. Okay? That's one thing you will see apart. When you do this emission, when you do the ionization, this is something else you can see. And that is X-ray fluorescence. Now you will see something else. That is even more interesting. This is not the way it really happens, but I am going to simplify it for you, just for you to get a feel for it. But what actually happens is something else. But let's see what happens. I remove the electron from here. It's gone. I have a hole. What can happen? This fellow jumps here. What can happen? HU is emitted. And if that HU is good enough to keep this guy out, this guy is gone. So basically this is called a secondary electron emission. So you keep this electron out, this fellow jumps in, gives me a photon, and I can now consider that this photon acts as a source for the next ionization, keeping this guy out, and now you will see a second bunch of electrons, which are actually not the ones that you created in the first place, it is the one that the system has now created in the first place, in the second place, by the light that was emitted by this jump. And that, these bunch of electrons that you get have a very special name to it. Auger. You will hear people giving various names, auger and ogre and all that. There is no ogre or auger. It's Auger spectroscopy. And Auger spectroscopy, mind you, and what is the electron energy of Auger spectra going to be? This fellow's kinetic energy, what is that going to be? It is going to be this difference in energy minus this, right? It is this difference, which is the h nu, kicking this guy out. Therefore, it is this difference minus this, and therefore it has to be very unique to the element in question. The electron, Auger electron kinetic energy does not depend on your h nu. Your h nu decides what the photoelectron kinetic energy will be for this guy to go out. But once this guy has, or this guy to go out, once this guy has gone out, what happens? This guy jumps, fixed energy now, because this orbital and this orbital is unique for that metal, and that energy actually kicks this guy out, which is also fixed, and therefore, irrespective of what photon energy you used, the Auger electron energy will not change, because the Auger electron energy depends on this difference minus this difference, and your photon energy never comes into play. Your photon energy decides the kinetic energy of the first electron that went out. After that, the Auger electron energy does not depend on what photon you used. Therefore, it is extremely insensitive. You can use UV, 40 eV UV, 16 UV UV, nothing, doesn't matter. You will find that the Auger electron for a given element is going to be fixed, and that's wonderful. Because if I measure Auger electron spectra, I can tell you exactly, without having to worry about the wavelength of light I am using, I can tell you what the element is. And that's the nice thing about Auger electron spectroscopy. So you can see what happens. The moment you kick an electron out of the orbital, there are a whole series of acts that can go. The whole drama is very complicated. You get photoelectron spectra to begin with. You can have, if you kick this guy out, you can have X-ray fluorescence. You kick this guy out, you have X-ray, this guy jumps in and kicks this guy out, you have Auger. So just this one act of kicking one electron out actually causes a cascade of processes inside that element or the molecule. And you can have Auger, you can have X-ray fluorescence, you can have photoelectron spectroscopy, all of it happening at the same time. So if you're really smart, you can build one photoelectron spectrometer and have all these features in it. You can do photoelectron spectroscopy.